So, welcome back. We're in the middle of sources of parallelism, and let me give you a summary of what we did last time and then continue where we left off and hopefully finish this topic today. So the things we need to do in order to write fast parallel simulations is we have to find a lot of parallelism, get lots of things to run independently, and we also have to worry about locality. The data that each processor accesses is as local as possible. It doesn't have to communicate with other stuff. And the point of all these examples is that arises naturally. There's certain patterns that come up in all these simulations, and if you just take advantage of it, you'll get it automatically. So far I've talked about discrete event simulation, and I'm in the middle of that, where everything is discrete. Time is going in discrete steps, and the things that you're simulating, there's a discrete number of them. And next I'll get to particle systems, lumped variables, which is ODEs, and continuous variables, which is PDEs. So here's where I was in the middle of discrete event simulation. The standard examples are the game of life, or digital circuits where you have AND gates and OR gates and everything is 0 or 1, or games like Pac-Man, or financial transactions. And so there's a finite set of variables, and if you take all their values at any time, that's called the state. And you want to update that state, and that's done by something called a transition function. So each variable is updated by a function which depends on some other variables, and at certain time steps, you get a new value. There are two ways to do these kinds of simulations. The simplest one is synchronous. So the canonical example is your computer. There's a clock, and at every time step, every nanosecond, you get some information and everybody updates at the same time. And we talked about how to parallelize that. The big issue is making sure that everybody gets an equal number of states to update. That's pretty easy. But then you also have to minimize communication. Make sure that you don't have to talk to too many other processors. And we define that as a graph partitioning problem, or dividing things up so you're minimizing a surface to volume ratio. That's a pattern we'll see again today. And the other kind of simulation, which can be much more efficient, is called asynchronous. And there you only bother updating a value if its inputs change. Not everything changes at the same time, so it's not worth re-updating things that change rarely. And so you only do it when an event occurs, and that's called event-driven simulation. So let's go on and talk about that asynchronous simulation. Again, so as I just said, the synchronous one can waste a lot of time because if the inputs don't change, why bother updating the value, the output, which won't change? So now we're only going to do it when there's an event that occurs. So there's no global time steps anymore. So each event, when it goes from one process to another, or from one variable to another, has to have a timestamp associated with it, so you know what time to use it at. So we had an example which was a game of life where you have loosely connected ponds, and so a fish very rarely swims from one pond to another, so you don't bother doing it unless somebody shows up. Circuit simulation, where you have delays in the gates, right? Not every gate changes every time step, so you have delays. And then in traffic simulation, you may have cars changing lanes. If a car doesn't change a lane for a long time, then there are certain things that won't occur. So asynchronous can be much more efficient, but it's going to be harder to parallelize, and there are going to be two approaches. And the basic idea is, how do you know when to ask, when your neighbor has sent you something and how to change? So there are two ways to go. And again, this is a little bit of a review. There's the conservative approach and the speculative approach. And the conservative approach says you look at all of your inputs from all of the guys you depend on, and if all of those have been updated up to time t equals 10, say, then you know you are allowed to compute up to time t equals 10. You can't go any further and be sure you get the right answer, because something may happen at time 10 plus 0.01, right? But you're good up to 10 if all of your inputs are updated to time 10. The trouble with that approach is you can get deadlock. And I'll have an example on the next slide. The other one, which is more speculative, is maybe all your inputs have been updated up to time 10, and you say, I don't think they're going to change. I'll go up to time 15. So what if you get to time 15 and one of your neighbors says, oops, one of your inputs changed back at time 11? What you have to do is back up. You have to have made a copy of what happened back at time 10, go back, and then resimulate forward. If that doesn't happen very often, and there are a lot of cases where it doesn't, then you're going to make a lot of progress. Both of these are used in practice, so the conservative approach appears in this particular circuit simulator, PTHOR, and the other one appears in a different circuit simulator. So one size does not fit all. So in all these cases, you have to optimize both load balance and locality, and that's going to be a challenge in all of these cases. So locality means if you have let's say a sub-circuit, and everybody's interacting a lot with one another and the rest of the circuit is quiet, then if you don't want to communicate very much, you put that whole active circuit on one processor because they all influence one another. You don't have to talk to anybody else. But in that case, the load balance is bad because all the action is happening in one place. So these are just, this is life and you have to balance it out. So let me give you an example of how you get into a deadlock and how you fix it. So let's suppose we just have 3 ponds in which there are fish swimming around, and they're only allowed to swim in this direction. So just to make it easy. So let's suppose that everybody has simulated the state of their fish up to time t0. Nobody's moved, and so everybody's waiting. Everybody's sitting there saying, you know, I can't go past time t0. Nobody else can go past time t0, so everybody's just waiting, and it's a deadlock. So what do? So after you've been stuck for a while, you think, maybe I'm stuck. I'm going to send a message to my neighbor which says, are you stuck too at time t0? And if you get a message like that, you send it to your neighbor. You forward it saying, my neighbor is stuck at time t0. Now, if that message goes all the way around in a circle and comes back to you and you get a copy of your own message, you know there's a deadlock. And at that point, everybody says, oh, I'm going to take a step forward, and everybody can move. And you can tell that if this happens too often, it's a very slow serial bottleneck, and it's not a good idea. So this is only, of course, a good idea for some particular kinds of simulations. Okay. So that's all I wanted to say about discrete event simulation. And everything is discrete. Time is discrete. Space is discrete. How do you divide things up? You take your domain. If things are connected to neighbors, which they often are, you decompose the domain in some physical sense, minimizing the surface to volume ratio of the bricks. We drew a picture where you broke it up into squares, and everybody only had to talk to their neighbors, their neighboring squares. And then we had either synchronous simulation, everybody jumps ahead at a timestamp, or the asynchronous kind, where you could either be conservative and possibly get deadlocks. You only simulate up to the time where you know the inputs, versus just being a gambler, speculating, going ahead, and having to back up if necessary. So, are there any questions about discrete events before we go on to particles, which is, you know, getting the next step of continuity in this? Okay. So a particle system has a finite number of particles that are moving around, and so in that sense it still is discrete like the discrete event simulation, but now their positions are all changing continuously with time. And the easiest thing to think of is, you know, Newton's laws, F equals ma. So here are canonical examples that come up all the time. So stars in space moving under gravity. A star is modeled as a point mass moving around. An electron beam in semiconductor manufacturing, so the particles are electrons and they have forces on them from all the electrostatics. Atoms in a molecule, again, electrostatic forces. Neutrons, so no electrostatic forces anymore, but they're bouncing off of things in the reactor as they move around. Sometimes you can do cars on a freeway, you're moving ahead, plus you might have to add a model of the driver and the engine as to what's going on, but other than that, it's just sort of particles moving along. And then balls in a pinball game, which indeed is going to be one of your assignments. So this is what it looks like, and it's pretty clear that if I'm a particle and I know the force on myself, I can use Newton's law to compute the acceleration, and I can figure out where to go for a little while. And so and that's all embarrassingly parallel. The tricky part is everybody needs to know the force on themselves. So what we're going to do is break down the force into 3 components, and each component is going to get parallelized differently, depending on the physics. So there's external force, there's nearby force, which only depends on your neighbors, and then there's far field force, like gravity, where everybody depends on everybody. That's the interesting, most challenging one. So the external force, for example, might be the ocean current in sharks and fish. Everybody knows, depending on their coordinates, what the external force on them is from the ocean. That's very easy to do. And if you have an externally imposed electric field on an electron beam, again, everybody knows, just based on where they are, they can independently say, what's the force on me due to the externally imposed field? So what about nearby forces? Again, in sharks and fish, sharks are attracted to nearby fish for, hungry reasons, and if it's a far away fish, they don't care about it. Bouncing balls is another canonical example, only if they touch one another, and that's as close as you get, and they bounce, and that's another example. But in physics, there's another force called van der Waals force, which is sort of trying to model dipoles and multipole attractions, and it happens to decrease like 1 over r to the 6th, right? If it were gravity, it would be 1 over r squared. Everybody depends on everybody. 1 over r to the 6th decreases so fast you basically ignore it once r gets past a certain size. And this has been in the news in the last few years because that's how people think gecko feet work. So geckos are these cute little creatures that can walk upside down or up glass and so forth. And people think it's the van der Waals forces in their feet that can attract and sort of let go automatically whenever they feel like it. And then finally, there's far field force, where everybody's attracted to everybody else, like an inverse square law. And so gravity, electrostatics, in computer graphics, it's called radiosity. And in this case, all these forces are governed by differential equations. They're called elliptic partial differential equations. And we're going to use that fact later to sort of come up with fast algorithms for evaluating it. Because the obvious way to do it when everybody has to talk to everybody is going to be n squared. And we want to do it much cheaper than that. So let me give you the simplest example, because it's only a few lines of MATLAB, of what if you only have external current, just to make it clear that it's embarrassingly parallel. So here's some very simple MATLAB code that takes an array of fish positions. So it's just an array. So fish P of 1 is where fish 1 is. Fish P sub 2 is where fish 2 is. And I'll store it as a single number, a single complex number, xy coordinates, real imaginary. So I get an array of positions, an array of velocities, an array of masses, and I want to simulate all these guys moving forward from time t equals 0 to time t final. And so this is the sort of simplest algorithm you can imagine. If you've had a numerical analysis class, it's called Euler's method, but basically everybody goes in a straight line for a tiny time step. So what I'm going to do is I'm going to loop starting from time t equals 0. I'm going to take little time steps, start with, a hundredth of a second. If I know my velocity, I'm going to move in a straight line for just that little, 1/100th of a second, update my position. Then, once I know my position, I can do F equals ma, divide the current by the mass, get my acceleration, and then use the same simple formula to update the velocity. The velocity is going to move in a straight line for a hundredth of a second and change by the acceleration. So that's the simplest kind of algorithm that you could imagine. There are more numerically sophisticated ones, but from a parallelism point of view, we don't care. This captures all you need to know. So this is all embarrassingly parallel. Finally, we have some coordination, some communication involved, and that's computing the time step. Because I don't want to get the time step so big because I could get a wrong answer. So what's a typical rule? The typical rule is, please don't take such a big time step that the velocity changes by more than, say, 10%. So what I got to do is take the largest velocity, so that's the max absolute value of all the velocities, that's communication, divide it by the max absolute acceleration, multiply it by 0.1, and that tells me the time step. So this is, sort of a toy example, but that's where the communication would come from in this. So here is the parallelism of the external forces, sort of summarizing from that example. This is all embarrassingly parallel. It's sometimes called MapReduce by analogy. The word embarrassingly parallel has been replaced by that. So all you have to do it perfectly is evenly distribute the particles on the processors. Any distribution works. Locality is not an issue at all because nobody communicates. The only thing you have to do is a reduction, that's the reduce part, to compute, say, the min of all of these ratios to get the time step. So that's the easy thing to do. So we're going to go to the next more interesting force, which is nearby forces. And so now I do depend on my nearby neighbors, and so now I do have to communicate. And the easiest thing to think about is bouncing balls. And so the simplest algorithm you could imagine is everybody has to look at every ball. Every one of the n balls has to look at all the others to see if they're close enough together. And so it's n squared work. That's a bad idea. It's much easier and better if we divide up the domain. So suppose everybody's living in this big square domain, and suppose I have 25 processors, and I'm arranging them in this 5x5 grid of processors, and each processor is simply going to own all the particles that happen to be inside that domain, and so they only have to simulate what's going on in there. And so now that gives you good parallelism. Everybody only has n over p processors, and the question is, what about the communication? So I want to communicate as little as possible. And so it's pretty clear if these particles are moving around, like, say, this guy, he's in the middle of the domain. He doesn't have to look at any other processor's particles in order to figure out if he's going to bounce off of them, because he's so far away from all the other processors. It gets interesting when you're right near the border here in this ghost zone, so-called ghost zone that I've colored light blue. He's close enough that he could bounce off of somebody in the other processor. So what you have to do is communicate everybody close enough to your border in your ghost zone with your neighbors. And then, only then do you have to check for collisions. So you only have to send all the particles in these skinny little neighborhoods to your 1, 2, 3, 4, 5, 6, 7, 8 neighbors. And so that's So the question is, what shape do I pick these domains in? We had the same question last time. Squares seem natural, but I could also have just horizontal bands. I could have had P sort of strips across. But what we want to do is minimize communication. That means minimize the surface to volume ratio. I want to have the area, in this case, of all of those light blue bands to be as small as possible, and squares are as good as I can do. Okay, so that is how we're going to minimize communication, but it's not necessarily load balanced, right? So I took this whole domain and I kind of assumed that all the particles were spread out uniformly, but the particles could cluster, right? I have to deal with a case of particles clustering. So here's how you deal with that problem. Well, how do you balance the load if particles cluster? So here are the particles, and you can see they're not uniformly distributed. So here is sort of the simple recursive algorithm. It's called a quad tree. So the first thing I'll do is I'll break up my big domain into 4 small domains, 4 small squares, by drawing those 2 lines. And I'll look at each one of those and I'll say, is there enough in there? So here there are only 2. Here there are only 2, so I'm done. One processor will own those 2. But there's still lots left here, so I have to keep on dividing. So let me go over into this domain. I'll divide it again into 4. And now that region gets 1 processor, that one gets 1, that one doesn't have anybody, so I don't have to assign any work there, and it's still crowded here. So I just keep on dividing into these subsquares. It's called a quad tree. And finally I stop when each square has 1 or 2, has at most 3 particles. And this is sort of the same idea. I'm still minimizing the surface to volume ratio roughly, and every processor is finally assigned about an equal amount of work to do. And I've drawn this in 2 dimensions, so it's called a quad tree. And if it were in 3 dimensions, I'd break it up into cubes, and it would be called an octree. And so this is a perfectly typical way to solve the second challenge. So any questions about nearby forces? The next one is yes. And let me ask the microphone. Front row.
So if after several time steps, the locations of each of the particles may change dramatically.
Right. So absolutely. And so that is a challenge I was going to list on my last slide, but since you brought it up, how often do you have to repartition it? Right. So what happens now, if this particle moves into that processor, let it move, and that processor now becomes responsible. I can do that for a while, but eventually it may get unbalanced. And so what you need to do is keep track of the global imbalance, and when it gets above a threshold, you need to rebuild all of it. Hopefully that doesn't happen very often, but it's a balancing game, right? You'll have to pay a price for that, but you may pay a price for not balancing it. So life is trade-offs.
Okay, cool.
Okay, finally we get to the hardest case and the most interesting case, which is far field forces, where in principle everybody depends on everybody. And so gravity and the electrostatics and protein folding and so forth. And the simplest algorithm is n squared, right? Every particle has to be combined with the data from another one to say what's the force on particle I from particle j. And so the simplest algorithm you could imagine is the following one. Suppose I have here 5 processors, so each processor owns n over 5 particles. And so at each time step, this is what happens. You take all the particles that you own, and you compute all possible interactions. So that's n divided by 5 squared interactions just using your local processors, your local particles. What happens next? You take a copy of your particles and send them to your neighbor. Everybody does that. This guy sends a copy of his particles to him, his particles get sent to him, and around in a circle. So now what you do is you take your neighbor's n over 5 and your n over 5 and compute all possible interactions of them. That takes a while. Then you keep going around and keep sending your neighbor's particles to your neighbor's particles, and eventually every set of particles has been everywhere once, and you're done. And if you count how much communication that is, well, every chunk of n over p particles has been sent to a neighbor p times, so the total number of words moved is n over p times p, or n. So that doesn't sound very good, and the good news is there's lots of much more clever algorithms that do arbitrarily better than that. So even if you want to compute all n squared interactions, I can do much better with communication, and we'll talk about that later. But even better, you can beat n squared. You don't have to compute all possible n squared interactions. In fact, you can do it in order n, by taking advantage of the mathematical structure of the forces. And so let me just give you two examples, because there's going to be a whole lecture later in the semester on this. This is kind of a tour. So the two ways to get from n squared to order n, the first one is called particle mesh. And all of these rely on approximations. And so here's the idea. I'm going to take all my particles, and now I'm going to superimpose a mesh. So this is now not processor boundaries, but it's a sort of a regular mesh. And what I'm going to do is I'm going to take each particle and move it to the nearest mesh point. So I'm going to take my original distribution of particles and approximate it by particles that only live at these mesh points. Now, why would I do that? The answer is that the solution to that problem becomes much easier if the particles are sitting on a mesh, because there are algorithms like the fast Fourier transform in multigrid that solve a particular differential equation called the Poisson equation that tells you the answer when everybody's sitting on regular grid points. So that gives me the right answer for this approximate problem where the particles are sitting at these places. And then what I need to do is go back and interpolate. So I know the forces there, and there, and I'll just interpolate to get the forces on the original locations. So that's an approximation, but the payoff is going from n squared to n log n, or n. So here are the three steps. I have to take each particle, and I move them to the nearest mesh point. That's called a scatter operation. There's communication there. Then I solve the problem on a mesh, and we'll talk about FFTs and multigrid later. And then I have to do interpolation, and that's called a gather. Everybody has to get data from their neighboring mesh points. And so that's one way to do it. But here's another way to do it, which is based on a different kind of approximation and doesn't require nearby mesh points or anything. And the idea is that, and I've used this analogy before, anything that's far enough away just gets simpler. So if I want the force on the Earth from everybody in the universe, and I go up and look at the stars at night, and there's one bright star out there that I suddenly realize is the Andromeda Galaxy, which has another billion stars inside of it, my first impression was correct. I can approximate that bright dot of the Andromeda Galaxy by its center of mass approximation. I don't need to have sums for every star in the Andromeda Galaxy. And conversely, the Milky Way looks like a dot when you're in the Andromeda Galaxy. And so by using that approximation recursively, and inside the Andromeda Galaxy you do the same thing, then the algorithms go from n squared to n log n. And this was such a great idea. It's been rediscovered in various forms. The most famous and general version is called the fast multipole method of Greengard and Rocklin. It was such a good idea that it got the two authors into 3 national academies. So we'll talk about how that works too. It's been incredibly useful for many fields, and we'll talk about that in a later lecture. Okay. So let me summarize particle methods. So I'm obviously giving lots of forward pointers to later lectures, but this is meant to be just in general how you deal with this. So the model has discrete entities, namely particles, so that much of it's discrete, but now the time and the positions of the particles is continuous, and I have to discretize time. I'm only going to compute their locations at discrete time steps, time 1, 2, 3. And so all the interesting stuff comes in computing the forces. I broke it up into 3 parts, external, nearby, and far field. And the obvious way to do it when everybody depends on everybody is to pair them all up, and it costs me n squared. I don't want to do that. And I described 2 much faster methods, particle mesh, where everybody gets approximated by moving to a nearby regular mesh point, and these tree-based algorithms. And so, anyway, and we'll follow up on that later. So are there any questions about particle methods before I go on to the next high-level simulation problem? Okay. So the one I just talked about you can think of as a special case of these lumped systems or ordinary differential equations. So in this case, many systems can be approximated by, you have a list of variables, you have a finite list of variables, particle positions are just one, and each one depends on some continuous parameter, usually time, and some function of all of its neighbors. And so a canonical example would be simulating a circuit at the level of SPICE if you're an electrical engineer. And so I'm going to use a common model for all of these things. I'm going to approximate the thing I'm simulating as a graph. A graph, as you may have studied in a computer science class. So what's a graph? There are a bunch of vertices or nodes, and there are a bunch of edges connecting those nodes. And so that's a simple abstract thing. In the case of a circuit, the nodes are places where wires come together. The edges are the wires themselves, so that's a natural way to describe a circuit. But in addition, each edge has some interesting property. It may have a resistor on it, or a capacitor, or an inductor. It has some property. Okay? And so we're going to call this system lumped because we're not computing the voltage at every point along the wire. We don't care about that. We only want the voltage and the current at the nodes, where the wires come together. That's all we need to know. And so now I need to relate all of those voltages and currents at all of those points, that discrete list. And there's, depending on your problem, there's laws of physics that tell you how to write down the equations. And so if it's a circuit, you have Ohm's laws, Kirchhoff's laws, all that kind of stuff. And if you're a mechanical engineer, you have F equals ma and Hooke's law, and I'll show you some more examples there. So when you write it all down, what do you get? You often get a system of ordinary differential equations, or ODEs. But that's not all you get, because some of these physical laws may not have any derivatives in them. They may just be conservation, that certain things add up to certain other things. So you may just get plain old algebraic equations. So altogether, they're called differential algebraic equations. And so let me just give two examples in a little bit more detail to show you what they look like. And the first one, again, is about circuits. So just imagine a circuit, as I described before, with a bunch of wires connected, and there's some resistors and capacitors. So what do I need to know? I have a finite list of things, which is what is the voltage at each node where all the wires come together? What is the current going along each edge? And what is the branch voltage? That's the difference between the voltage at two ends of a wire. So that's a finite list of stuff. And if I know all of those, I know everything I need to know about my circuit. And then, what are my equations? There's 5 laws of physics or of electrical engineering that I write down that tells me everything I need to know. So here's and I've written it down here as a matrix times a vector equals a vector. But this matrix has some derivatives in it, so it's really a differential equation. So here's my array of node voltages, and branch currents. And the first law is simply Kirchhoff's current law, which says that all the electrons that flow into a point have to flow out again, right? So conservation of electrons. And I can write that down simply by saying all the current going in has to add up to all the current going out of every point. And so all I need to do is take the appropriate linear combinations of all these currents and add them up and set it equal to 0. And that's all captured in this sparse matrix. So this matrix, capital A, is a very sparse matrix. There's one column for every edge, for every wire in the circuit. There's one row for every node where the wires come together, and there's just a bunch of plus ones and minus ones saying who's connected to whom. And by multiplying this matrix of plus minus ones times the currents and saying it equals 0, it just sort of captures that conservation law. So big sparse matrices, this is not the first time you'll see them. They come up all over the place as sort of natural data structures. The next one is the voltage law, and it's simple. It says that the edge, the voltage along an edge is just the difference of the voltages at the endpoints. So it's the same matrix except it's transpose. And then there's Ohm's law, which says resistance times current equals voltage. That's all natural. And finally, I get to the derivatives where I have capacitance and inductance, and now I have to differentiate currents and voltages, and that's where the differential equations come from. So I can write it down as a single large system. So just to change an example, so here's one that, again, your life depends on. Here's the section of the freeway that I think fell down in that earthquake. And needless to say, these are the things that civil engineers like to do big simulations of to make sure it doesn't happen again, or how do they design it. So now my variables are not currents and voltages, they're the displacements, they're the positions of points in a building or in a stretch of freeway. I don't use Kirchhoff's laws anymore. I use F equals ma and Hooke's laws, which is spring constants. How much the force depends on how much you displace it. And so what kind of modeling do people do when you write down all the equations? There's static modeling, which says I'm going to exert a particular force on one part of the building. How much does it all move? That's solving systems of linear equations. I could do dynamic modeling, which is where I input a force like an earthquake, and then I get my differential equation, and I solve it. And that tells me where the thing moves. And finally, you get eigenvalue problems. And that's another linear algebra problem. So I take that big matrix that describes my movement of this stretch of freeway, and I ask, what are its eigenvalues? And what are eigenvalues good for? Well, they tell you how the building likes to resonate, right? If you push the building at that frequency, it will go into resonance. And then you ask, do earthquakes vibrate at the same frequency? Because if the frequency of the earthquake matches the resonant frequency of the building, well, you can imagine what will happen. And so you don't want your eigenvalues to be wrong. And so we have to solve those problems too, and there's a big parallel computing project here in civil engineering that builds tools for this kind of stuff. And so finally, let me show another example, which people around the world use every day, whether they know it or not. And it's Star Wars, The Force Unleashed. Which was developed here by James O'Brien and released by Pixar. So in this case, let me turn down the sound a little bit. Whenever Darth Vader smashes something, it's doing real-time, parallel, finite element analysis to get the physics right enough, so you can see what he's smashing. So it has finite element models of all the materials in the game, and so whenever you, the player, hit something, it does the physics. And so let me just show you a few examples here of where this is going. So we don't have to watch the whole video. You're welcome to, because I put up the URL. So here's the different materials just to illustrate. So stone has one particular property, so you can see that it has fracture mechanics and all of that built in. And it has to generate the sound correctly. So let me now move up to a different material. Okay. Glass is different, no surprise. Here's metal. It's stiffer and doesn't break quite so much, but it all has different models of metal inside of it. And you can do much softer material too. Like plants. So here, there's a lot of flexibility in them. They're not going to break so much. Well, maybe they'll break a little bit. So let's just see what happens here. Okay. The bark comes off. There we go. Okay, that's what happens. Can't get rid of the tree. So, and let me move up to show you one more level of detail to see what this looks like inside. Okay, so here is some of the gameplay. And now we're going to superimpose a finite element mesh. So this is what's inside the machine, inside your game box. And so whenever it smashes into something, it does the physics right. So let's just see what the mesh looks like. There we go. Now, if you don't like this particular set of material properties, you can change it, right? Because it's easy enough to do. So there, I'm just going to change the Young's modulus and possibly Poisson ratio. And now, it's not brick anymore. You can have any material you want. Anyway, so as you can imagine, this is widely used, whether you know it or not, this kind of parallel computing. So this is all running in parallel on an Xbox. Okay. So, any questions about this one? I recommend, James O'Brien if you want to know what the next thing to do is in this area to make even more realistic graphics. Okay, so all of these come down to solving ordinary differential equations. And in all cases, most of the information is captured in a sparse matrix. So one example that I showed you was specifically from writing down the circuit equation. And that just represented everybody who was connected to everybody else, and there aren't very many connections there. So most of the array entries are 0. And what we'd like to do is have algorithms that don't store all those zeros. That's a waste of space, and we certainly don't want to compute on them because that's a waste of time. So what we need are methods that will take advantage of all of those sparsity structures. So let me just give you a high-level view of what those algorithms look like. And in the case of ODEs, the two questions we want to solve are, solve the differential equation as a function of time. Move it, give me the state at time t in the future. There are two ways to do it, which have different numerical properties. They're called both explicit methods and implicit methods. They parallelize differently. And then finally, I'll just say a little bit about the modes of vibration problem, which are for eigenvalues. So let me do explicit methods first. Those are the easiest to parallelize, but they have some numerical drawbacks. So let me take the simplest possible ordinary differential equation, so x prime of t equals f of x, and let me just suppose it's sparse matrix A times x. It could be more complicated than that, but this captures all you need to know to talk about the parallelism. So what does this mean? This tells me that if I have the solution at time t sub I, and I want the solution at time t sub I plus 1, then the ordinary differential equation tells me how to do it because it tells me the slope of the solution. It tells me the slope right there. So to go from this point here, x sub I, up to x sub I plus 1, I add the time step, the horizontal step times the slope, right? So it's the simplest possible approximation. So the question is, where do I get the slope from? And the choice I'm going to make here is I'm going to use the explicit method. I'm going to use the slope right there. So it's the tangent to the solution at the beginning of the interval. And that's called Euler's method. And when you write it down, it's going to be x sub I plus 1 is x sub I plus dt times the slope. And the slope is, given by the differential equation, it's a times x sub I. So this is take a vector and add to it a scalar times a matrix times a vector. It's all in sparse matrix vector multiply. So all you need to parallelize this, even if it's nonlinear, it's the same idea, is a sparse matrix vector operation. So we will talk about how to parallelize this later. It's relatively simple, but it has a problem, which is that if this is very steep, if your solution is very steep, the technical term for that is stiff, then you can imagine you'd have to take very, very tiny time steps so that this blue line doesn't depart so much from the true solution. And so, in other words, if your matrix A has some really large entries, so it's very steep, you have to take a tiny time step. So we need a different way to deal with it. And so it's almost the same method. I'm still going to use the fact that the differential equation tells me the slope. So to get from time step I, the solution x sub I, to the solution x sub I plus 1, it's still going to be a straight line approximation. This blue thing is a straight line. But now I'm going to use the slope at the endpoint. I'm going to use the slope at the time step where I don't know the answer yet. This is called backward Euler, or an implicit method. So let me just write down the equation. So now I have the slope of this blue line. That's, the value at each endpoint divided by dt is going to be equal to the slope there. That's a times x sub I plus 1. So the difference between this slide and the last slide is I changed I to I plus 1. That's all I did. And if I rearrange that, if I solve this equation for the solution at x sub I plus 1, the solution there, that's what I want to know, I get a matrix times what I need to know is the solution at the current time step that I do know. This is a system of linear equations. And it's sparse and it's large. And so this is worse because solving a large sparse system of differential equations is more challenging than a matrix vector multiply, but now I can take much larger time steps. And depending on my problem, I might want to do that. So the patterns that we need to solve are either going to be sparse matrix vector multiply or solving large sparse systems of equations. So let me just say a couple words about eigenvalue problems because you've seen all the patterns you need. So now what I want are modes of vibration. And so what that means is that my differential equation is, for example, the second derivative of x with respect to time. The acceleration is, ma or something like that. So it's a times x. What I want to do is ask, is there a standing mode that solves this equation? Something that vibrates but keeps the shape the same. So I'm going to ask, is there a solution where it's just vibrating at some frequency omega times a fixed vector? So if I just plug that into this equation and solve, all the sine functions cancel out, and I get an eigenvalue problem. I get that I want x naught, the mode shape, is an eigenvector, and minus omega squared is an eigenvalue. So that tells me everything I need to know. And so what I need to do is find eigenvalues and eigenvectors of large sparse matrices. And the good news is that it all reduces to the same parallelization problems I had before. You spend all your time either doing sparse matrix vector multiply or solving large sparse systems of equations. And there's a question. So I'm just trying to motivate why we're going to talk about some of these patterns later.
Generally speaking, are sparse matrix multiplication and solving sparse linear system equivalent in terms of time?
No. So it's important to say that sparse matrix vector multiply is the cheapest thing you can do with a sparse matrix. You touch each entry once and you stream through it and you get the answer. But solving can be much, much more expensive. And there's a large collection of very clever algorithms that I'll give you a tour through. I won't talk about all of them in detail. But most of them, well, let me go to the next slide and just talk about that. There are two ways to do it. There are both direct methods for solving those large sparse systems, and there's iterative methods. And the direct methods are basically all variations in Gaussian elimination, which is something we learned about a long time ago. The language for it is called LU decomposition, because what we actually do is we take our big sparse matrix and we factor it into the product of a lower triangular sparse matrix and an upper triangular sparse matrix. So that's how I'll describe the algorithm later. What's tricky, of course, is that you only want to operate on the non-zero entries. It's also more complicated because when you do Gaussian elimination, you add multiples of one row to another in the naive approach, you get lots of new non-zero entries that weren't there before. And so there's lots of cleverness required to minimize that. Those are direct methods, and they have their pluses and minuses. But if your problem is so big that you can't afford to do these, then what you do is reduce it to sparse matrix vector multiply. You do lots and lots of sparse matrix vector multiplies, and by taking, and doing that cleverly, there's a lot of classical algorithms, conjugate gradients, multigrid, you get the answer. It doesn't give you the right answer immediately, it converges at some rate. And so again, I'll just sketch those. But since they all depend on accessing sparse matrices, let me now tell you what is the basic data structure for sparse matrices and how do we parallelize the most basic operation, which is sparse matrix vector multiply. So there are an awful lot of data structures for sparse matrices, but here is the classical one and we'll talk about fancier ones later in the semester. So SPMV is short for sparse matrix vector multiply. And here's my matrix A, and it's coded so that all the white entries are zeros. I don't want to store them. And all the colored entries are the non-zeros that I do want to store. And I want to do y equals y plus this matrix A times x. And so the simplest possible data structure that stores as little data as possible is simply to take all the non-zeros and all the rows and just pack them together. Throw away the zeros. So these 4 non-zeros in the first row will get packed together, followed by the 3 non-zeros in the second row, and I can't use any less storage than that to keep track of all the non-zeros. But if that's all I do, I've forgotten where they are, so I need another array, the index array, which remembers what column they were in. So for example, this is in column 1, 2, 5, 8, so these numbers are 1, 2, 5, 8. And so each row of those will keep track of that. And finally, I have to remember where each row begins and each row ends, so I need one last pointer array which points to the beginning of each row. And so that's going to be my data structure, my simplest possible data structure. And so I want to talk about how am I going to implement this kernel here. So I just need to execute this particular operation over and over again, but I only want to do it for the non-zeros. And so here it is. It's a very simple 2 nested loops. I'm going to iterate over each row for the rows going from 1 down to the bottom, so 1 through 6. And then I will iterate over all of the non-zeros in each entry, which means I'll go from the beginning of each row to the end, from pointer sub I to this guy minus 1. And I will I'll multiply the value that I grab from the array, so that's the matrix entry, and then I have to multiply it by x. But which x? I have to go get x sub 1, x sub 2, x sub 5, x sub 8. So I have this index array that's going to irregularly access entries of x. So I have this indirect addressing, which is going to be an issue to make that run fast. Okay. And we'll try to deal with it, but this is the most basic data structure. So how do I parallelize that? And so let me tell you the simplest way to do it, and what are the issues. So here I've drawn my matrix again, so I want to do matrix A times x equals y. And suppose I have 4 processors. A natural thing to do is to simply say each processor gets 1/4 of the rows, and 1/4 of the rows of y, and 1/4 of x. But I have some decisions to make, which is, which quarter, right? I don't necessarily want to give the first quarter of the rows to processor 1 and the next quarter of the rows to processor 2. I want to make sure I'm balancing the work as well as I can, and I also want to make sure I'm minimizing communication. So here's the general way I want to do it. What I need to do is take all of the rows of the matrix, their index from 1 to n, and partition it into p sets. So this is a subset of 1 through n. Processor 1 will get those, processor 2 will get those. I need to pick those in a clever way. I'll talk about what that means in the next slide. But once I've assigned those rows to each processor, processor K is going to store the corresponding entries of y, the corresponding entries of x, And then it will be responsible for doing the matrix vector multiply. It's going to do the dot product of each row of A that it owns with all of X. That's where the communication comes in. I'm probably going to have to communicate X's from some processors to other processors in order to do the dot products. And so, but each processor is responsible for computing the entries of Y that it owns. So it's called the owner computes rule. So the question is, how do I do this partitioning? So let's ask what would be diagonal, what would be ideal if my matrix were block diagonal, if I could reorder the rows, the rows of the matrix so it looked like this. This is incredibly special. This would be perfect. No communication would be required. Every processor, and so if all the non-zeros were in the diagonal blocks, processor 0 would multiply its local chunk of A times its local chunk of X and get its local chunk of Y. Everybody would be load balanced, and there'd be no communication. So most matrices don't look like this, right? There are going to be lots of non-zeros scattered all over the place. And the question is, how do I pick the right ordering so that it looks as much like this as possible? Now, it turns out that we talked about this already. So here, let me just summarize those performance goals. So I want to balance the load. I want every processor to have an equal amount of work to do. And what's the work? The work is the number of multiplies and adds. So that means everybody should have about an equal number of non-zeros. That doesn't mean an equal number of rows, right? Because some rows may have more non-zeros than others. I want to balance the storage, balance the memory. That's the same thing. Number of non-zeros tells you the memory. I want to minimize the communication. And that means I want to have most of the stuff on the diagonal and as few non-zeros out here as possible. And then I want to, do local optimizations too to improve cache locality. And so that means I'm going to do even more reordering, and we'll have a lecture on that later. And so what I want to do is ask, just for these first three parts, how do I balance the load and minimize communication? And we're going to see it's the problem I talked about in the last lecture. It's called the graph partitioning problem. So that came up in the discrete event simulation. It's going to come up here too. So let me just remind you of this language. I'm going to use two languages sort of interchangeably during the semester, which is sparse matrices and graphs. And these are completely isomorphic. I just want to make sure that we're all good with that language. So I can think of a graph with 6 vertices. I've drawn them all here. And some of them are connected by edges and some of them aren't. And I can represent that also as a sparse matrix. And if there's 6 nodes, it's a 6 by 6 matrix. And if there's an edge between vertices 2 and 4, that tells me that matrix entry 2, 4 is non-zero. I even color coordinated it. That blue guy corresponds to that blue 1, and 4, 2 is non-zero. So this is an undirected graph, so I get 4, 2 and 2, 4 are treated the same. So this matrix and this graph are isomorphic, and if I have different numbers in here, and I mean not every matrix entry has to be 1, then I'd have numbers associated with each edge. They'd be called edge weights. And so I will use these this way. So the question is, let's suppose I had 3 processors, and I want to assign vertices to processors. So let's suppose that I assign processor 1 gets vertices 3, 4, processor 2 gets vertices 1 and 2, and processor 3 gets vertices 5 and 6. So in the graph world, I've done this partitioning. And in the matrix world, that corresponds to this partitioning. So the question is this a good partitioning? Well, is it load balanced? What I need to do is count how many non-zeros there are in each block. So 1, 2, 3, 4, 5, 6, 7. I can do that counting. And for each one, and I can ask, is it load balanced? But I also want to minimize communication. So what's communication correspond to? It's how many of the non-zeros are out here that are connecting, let's say, yellow block 1 to yellow block 2. It's the orange, the blue, and the green. See, there's the orange. Let me get this right. The orange, the blue, and the green. Right? These edges connect this block to this block. Those represent communication, and they're stored out here. So what I want to do is pick these partitions to balance the load and minimize communication. And that is the graph partitioning problem that I talked about before. It comes up again. It comes up over and over again. It's NP complete. That means the only algorithm anybody knows to solve this problem perfectly is exponential in cost. It's much more expensive than the original problem. So we'll have lots of approximations that we talk about later. And there's lots of great software tools that solve this for you. Okay, so just to summarize the common problems that we've seen so far. So there's load balancing. And so I talked about that in the context of graph partitioning, where you have a fixed matrix, so you can spend your time solving the graph partitioning problem and just do it right once and for all. But I also mentioned that there's this dynamic problem. So if you're doing particles and they're moving around and they sort of all move from one cluster over here and they cluster in a different processor, you may have to change the load balance from time to time. And that's just a trade-off. Linear algebra came up in all sorts of examples, both dense and sparse, solving linear systems and eigenvalue problems. And I also talked about particle methods. So if I go back to this picture that I think I showed on the first day of class, these are the 7 dwarfs of high-performance computing. So I said there were these patterns that came up over and over again, which is the basis of this course. I'm teaching you to recognize these patterns, so you can say, oh, this is a solved problem. And so they were originally recognized in HPC high-performance computing, these red bricks here corresponding to dense matrices and sparse matrices and whatnot. I've just showed you where they came up. Right? We've seen dense matrix problems, sparse matrices. I mentioned FFTs briefly for the particle mesh method. N-body came up, and then the embarrassingly parallel MapReduce. And we'll get to structured grids and the other ones next time. And this picture represented that these patterns come up in machine learning and games and databases and everywhere else too. But I'm sort of emphasizing, most of the examples I just talked about are in high-performance computing. So that is the end of talking about lumped systems, or ODEs. So are there any questions before I go on to the next thing? Okay. So the final part of this 4-part lecture, I talked about discrete event simulation. I talked about particle methods. I talked about ODEs. And the final thing, so discrete event system, particle methods, ordinary differential equations, just did all those. And the last example is PDEs. And this is sort of a summary. The common problems that have come up over and over again, we'll see them again with PDEs, are load balancing, partitioning things to minimize communication, locality, and then the fact that there's a constant tension between these two, that if you optimize one, the other one may not be so good, and so you may have to dynamically change things as things move forward. So all of those will show up again when I talk about partial differential equations. So this is the last part. So there are 3 different kinds of partial differential equations that come up over and over again. I'm just going to pick one of them to illustrate things, but I want you to understand that these are the 3 kinds. There's elliptic problems, where everybody depends on everybody. It's sort of a steady state problem, and that's gravity and electrostatics. Then there's wave propagation. Those are called hyperbolic problems. So things are moving in time, so sound waves or vibrations. And there, things can't move faster than the speed of sound, or whatever the speed is. So you only depend on local information. So you only have local dependencies, so just basically from the physics. And then the last category is parabolic problems. That's what you call heat flow and diffusion. And there, everybody depends on everybody, but it's still moving ahead in time, right? So you want the temperature at every point in some, let's say, bar that's cold at one end and hot at the other. It's moving in time, but everybody depends on everybody. So this sort of, violates relativity, obviously, but this is what the mathematical model says, and that reflects the amount of communication that people do. So depending on whether you're solving elliptic or hyperbolic or parabolic problems, you may have global dependence, because everybody depends on everybody. And that either means you have a lot of communication, or in the case of heat, you may have to take tiny time steps. Or if you have finite propagation, speed of sound limits things, then you'll have just local dependencies. And of course, these are 3 model problems, and in the real world, if you're doing fluid flow, Navier-Stokes, if you're doing elasticity, you have combinations of all these that you have to put together. But just to illustrate, I'm going to pick the simplest possible one and talk about it. It'll show all the patterns that come up later. I'll show pretty pictures of more complicated ones. I'm just going to use the heat equation. And so I have a one-dimensional bar, which is red hot at one end, cold blue at the other. And I want to write down the equation for how does the temperature change in the middle. And so we can blame Fourier for this. He's the guy who invented this. And so I'm going to let U, as a function of, be the temperature. It's going to depend on where you are along the bar. That's x, and the time. And so what I want to do is write down an equation that the temperature has to satisfy. And what Fourier noticed was if you say, how fast is the temperature going to change at that point? So fix the point and ask, what's the rate of change of the temperature? It depends on the temperature gradient between there and there, and the temperature gradient between there and there. So, for example, if this is temperature 0 and that's 1, and this is -1 and that's 0, then the temperature gradient is the same on both sides. Nothing's going to change. You're going to stay at 0. And all of that is captured by this by this simple equation. This is the rate of change of the temperature in the middle. This is the temperature gradient here. This is the temperature gradient there. And this, if I subtract those two and divide by h, that's how much the temperature gradient is changing from there to there. And if I let h go to 0, which is what you do to do calculus, you get this differential equation. The rate of change is the second derivative of u with respect to x. So I want to now start from there and get an equation, an algorithm. And it's basically this one I had up here, but let me just write it down again. So what I need to do is take this continuous problem and make it discrete, because computers only do discrete things. So I'm going to solve it at discrete points in space, x1, x2, x3, and discrete points in time. And I'm just going to write down a formula that gets me from time t equals 0 to time t equals 1. So let me change the derivative of u with respect to time to a difference. So this is just approximating the slope by the secant. So there's the value at time t plus delta minus the value at time t divided by delta. When delta is small, that's a good approximation to the slope. And over here, it's the same formula that I had on the last slide. It's just a bunch of differences between the value of the temperature at a little bit to my left, right where I am, a little bit to my right, and dividing by the spacing. So let me now simplify that. A lot of terms cancel. And so there are really only three different terms. The temperature right where I am, a little bit to my left, a little bit to my right. And the thing is, I know my temperature where I am right now. I know everything at time t. I want to know the temperature in the future at time t plus delta. So all I have to do is solve this for the temperature in the future, and there's hardly anything to do. I just move this term over to that side, and this says the temperature at my position in the future is this particular linear combination of the temperatures right now, where I am, a little bit to my left and a little bit to my right. So it's a very simple formula. And if I just simplify the algebra a little bit, so this is just a constant, so let me just give that constant a name, then it's this very simple talking to my three neighbors. My value to the left, value to the right, myself, value to the right, and it really is just a matrix vector multiply in disguise, a sparse matrix vector multiply. And to see that, let me now discretize everything. I'm only going to be interested in the variables at x position equal to h, 2h, 3h, discrete values. I'm going to be interested in the time at delta, 2 delta, 3 delta. And so instead of having this continuous function, I'm going to have an array. And so the first subscript tells me space, the second subscript tells me time, and I'm going to be updating this array. And so finally, there's the formula. So I'm going to have a formula for how to update my array. I know all the temperatures at time I, and I want to know the temperatures at time I plus 1, and I just compute this linear combination. And so so this just repeats what I said before. I want the temperatures at time I and position j, and at each time so I'm going to have this array of temperatures. So what's the physics tell me? I mean, what do I need to know in order to solve this? Remember, it's the temperature inside a one-dimensional bar. Well, I have to know the temperature at the beginning at time t equals 0 or I equals 0. And I also have to know the temperature at the endpoints, right? Is one end of the bar in hot water and the other end of the bar in cold water. So I have to know the values along all the borders of this. And if I know that, this formula just tells me a way to update the value at each point given these three values. The temperature where I am now, a little bit to my left, a little bit to my right, I update into the future. And so given all this data, I get the next row of the array, the next row of the array, the next row of the array. And this is just a linear combination, so it's a sparse matrix vector multiply. And since it's a very special matrix that comes up over and over again, let me just write it down. So here's the formula that I just had, that everybody take a linear combination of three guys. And I'm going to write that as a matrix vector multiply, because that's all it is in disguise. And if I write down that matrix explicitly, there are only three numbers in each row, because I'm only taking a combination of three things. So I multiply this number times my location, z times my neighbor to the right, and z times my neighbor to the left. And there's z's all over the place, so let me pull that out. So there's one just down the diagonal, so I get an identity matrix. minus z times this matrix, this canonical matrix which shows up all the time in this business, 2's down the diagonal, minus 1's above, and minus 1's below. So I spend all my time doing a matrix vector multiply basically with this matrix. 2 times myself, negative 1 times my neighbors. And since every row of this matrix is the same, since I'm always doing the same thing, 2 times myself and subtracting my neighbors, it's called a stencil. Because everything, I take this row and I just copy it everywhere and I get the whole matrix. Here's another picture that people usually draw. So at each point, the stencil is take this number times myself and z times my neighbors and just repeat that everywhere. This matrix, it comes up over and over again, is called the Laplacian. And it comes up in continuous mathematics and discrete mathematics and everywhere else. So let me give it its due name, Laplacian. And this was just on a one-dimensional mesh. There's also a two-dimensional version of this. And in that case, this will be a little bit messier. I'll show you a picture of it later, but it's the same idea. There's something down the diagonal, and then there's some other diagonals that are filled in with minus 1's. Okay, so all of my time is going to be spent in the simplest possible algorithm in doing a sparse matrix vector multiply times this incredibly simple matrix. And so let me just talk about, remind you, I've said this before, what do I need to do to parallelize it? Well, I need to take all the points along my metal bar, which is to say all the rows of the matrix, and partition them. And this is very simple, because each row of the matrix has 3 non-zeros in it. And so it's perfectly load balanced if I give n over p consecutive rows to each processor. And this can work in arbitrary dimensions. And this is what people often do when they solve hyperbolic equations. Now, and because there's a finite wave speed and everything works out fine. But there's a problem that even though I sort of derived it for you and it works for the heat equation, it's really numerically unstable. So, and I'm going to just demonstrate that to you. What I mean is you have to take incredibly tiny time steps. So the time step is delta, and h is a distance between consecutive points. So if I divide, so it turns out that this system blows up if this ratio, if that number z that I showed you is bigger than a half. So what if I want to get a more accurate solution? What if I divide h by 10? Because I want 10 times the resolution. That means I have to divide the time steps by 100. So it gives me an incredibly strong limit. And so, but what happens if I don't do that? So let me just show you an example. So here I start with an iron bar that's cold at both ends, sitting in ice, and it's red hot in the middle. And so this axis, so the vertical axis is temperature. The horizontal axis is where I am along the bar, and the axis coming out of the page is time. So since the ends are in ice, it cools off, right? So eventually the whole thing turns blue because it's nice and cold. That's the solution you expect, and that's what the algorithm tells you if you pick that magic constant less than a half, 0.42. But what if I want to take a slightly bigger time step, not very much bigger? So it starts off fine, the bar is cooling off, but eventually it blows up for numerical reasons. And clearly this is the wrong answer. The temperature does not look like that, so I don't want to use this algorithm. It's still useful for your wave equations, but it's not going to be useful for the heat equation. So I have to use a different algorithm, which is going to parallelize differently. So let me go back to the original equation. There's the original heat equation. And I'm still going to discretize it. I'm just going to evaluate it for discrete values of x, x1, x2, x3, and discrete values of time. And so all I'm going to do is change the equation I had on the previous slide a little bit. On the previous slide, these red t plus deltas, they were just t's. I evaluated this thing. Now I'm evaluating it the future time step, t plus delta, and before I evaluated it at t. That's all I'm going to change. And now I'm going to solve this equation for the temperature at the new time step, t plus delta. But this is not quite so easy to solve as before. So if I move all the t plus deltas onto the one side of the equation, what I get here is something I know, the temperature at the current time. And on this side, I get a system of linear equations, right? So a linear combination of all the temperatures in the future. And so now I have to solve that system of linear equations. So let me discretize it the way I did before. I'm going to change my continuous function, which depends on x and t, to this array. So x is going to be just j times the spacing, and I is going to tell me the time, so delta, 2 delta, 3 delta. And so when I write down this equation, I get the temperature at time I on this side. I get the temperature at time I plus 1 on this side. And I get it's all multiplied by that same matrix, almost the same matrix I had before. So the I is the identity matrix, and L is the Laplacian. So this is a system of linear equations where the matrix in front is this tridiagonal matrix, and it's almost the same thing I had before. It depends on the Laplacian. Okay? So that means that in order to solve the heat equation, I have to solve this system of linear equations at every step. That will let me take very large time steps, and it'll be nice and numerically stable. I'll get the right answer. The price is I have to solve a system of linear equations at every step. So we solve this with ODEs too. Right? I could use the explicit method. It was a matrix vector multiply. Or I could use the implicit method, and it gave me better answers, but I had to solve a system of equations. So just to acknowledge the fact that in practice, what is the algorithm people actually use? They do both. They do a matrix vector multiply, and they do a solve. That's called the trapezoidal rule. So in practice, this is what people find has the best properties, and so you need to combine both, the explicit one and the implicit one. And this does the best job of getting you from time step I to time step I plus 1. And again, it all comes down to this Laplacian. So, and let me just say this, I'm mentioning this because if I were talking about gravity or electrostatics, I'd also be solving equations with Laplacian. It comes up everywhere. So let me just mention that. So this Poisson equation, so what's the Poisson equation? Solving Lx equal b, this Laplacian times x equals b. That comes up everywhere in gravity and electrostatics. And just to connect it to some basic physics that you may remember, what is the electrostatic force? Let's suppose I have a particle at a point x, y, z, and there's a particle at the origin, and they're attracting one another. What's the force on it? Well, it's an inverse square law. So it's the vector, it points from the particle back to the origin, and its length is 1 over r squared. If you take the norm of that vector, it's 1 over r squared. So the other thing, the way you can write that down, is to notice that the force is the gradient of the potential. There's a scalar function, that's a vector. There's a scalar function which is just 1 over r. And if you take its derivatives, it actually gives you this force. And so what people actually do in practice is they solve for the potential, and then they differentiate it and they get the force to move things around. And so this is just a basic recollection if you haven't seen it before, or to remind you of this basic physics. Okay, so I've told you all about the one-dimensional problem. What about the two-dimensional problem? Or the three-dimensional problem, for that matter, because that's where things get more interesting. In this case, this is the matrix. It is no longer a simple tridiagonal. It's gotten a little bit more complicated because what I have to do is take 4 times my own value and subtract all my nearest neighbors. So each row has 4 minus 1s in it. 4 times myself, minus 1 times my neighbor to the left and the right. Those are those 2 minus 1s. And minus 1s times my neighbor above me and below me. And those are farther away, right? Because I'm sort of ordering the mesh points from left to right. And so this is the matrix that I either have to multiply by or solve with. And this one is now gotten a lot more complicated. So what I'm going to do now is give you a one-slide summary of all the methods that people have tried to use for this. And I'm going to describe it in the form of a conversation, a typical conversation I have in office hours. So a student will come to my office and say, I need to solve a system of linear equations. And what I will typically say is, great, just use dense Gaussian elimination. Cost you n cubed, solve any problem that you want, and you're done. And then they tell me, well, that's not fast enough. And I say, well, tell me something more about your problem. And then they tell me, well, actually there are a lot of zeros in the matrix, and if you look at it far enough away from the band, from the diagonal, it's all zero. So it's really a band matrix. And the bandwidth, they tell me what the bandwidth is. And I say, oh, you should use band Gaussian elimination. You should be very happy. Your cost will go down from n cubed all the way down to n squared. That should make you happy now. And they say, it's still not fast enough. And then I say, well, tell me some more about your problem. And they say, well, I'm going to solve it over and over again with the same matrix with many, many right-hand sides. Can I take advantage of that? And I said, well, not really, because if I were to write down the explicit inverse and just multiply by it over and over again, that would still cost you n squared. You better tell me some more about your matrix. And then they tell me, well, it has this other property. It's symmetric, so really the upper half is the same as the lower half. And each row only has a few non-zeros in it. It's really, very sparse. There's only 4 non-zeros. And it also has this nice property called positive definite. That means all its eigenvalues are positive. And then I say, oh, there's this other class of grade algorithms. They're called conjugate gradients or red-black SOR. And that gets you the cost down from n squared to n to the 3 halves if you take advantage of those properties. And they say it's still not good enough. I say, well, what are you really trying to do? I say, well, I'm trying to solve the heat equation, right, on this 2-dimensional plate. And I say, why didn't you tell me? You should use either the FFT or multigrid, and the cost will go down to n log n or order n, right? And that's optimal. So depending on which properties your problem has, you may use any particular algorithm in this list. And the more you know about your problem, the more specific your algorithm can be. And so they all come up, right, in different points of time. And, somebody, in your team will hopefully have the expertise to choose the right one, but you have to be aware that one size does not fit all. So what I've done here is I've listed all these algorithms in order from the most general, works on any system of linear equations, to really works on matrices that look like Laplace's equation. And I've given you the runtime serial and in parallel where I'm counting communication is free. So it's sort of a very theoretical model. And it's an n by n system. And I've given you the answer when it's in the 2-dimensional problem and the 3-dimensional problem. Because I can have, temperature on a 2-dimensional plate or temperature in 3 dimensions. And it's slightly different. So 3D is in red. And each one uses different amounts of memory and different amount of processors. So anyway, over the course of the semester, I'll pick a few of these and talk about in a little bit more detail how they are parallelized. But they're all very useful. And all my comments that I just made here are on the next slide, which is, in which special cases each one work. But I don't want to say any more about it than that. Okay. So are there any questions about, yes, let me go back to that.
So this is more of a general question specifically on this material, but what you just said is exceedingly useful for people who don't know the domain. Is there a source to go to for this type of sort of meta information other than your slide deck?
Yes. So we have, for some of these, attempted to build decision trees, and we have pictures of them that say, here's the next question to ask about your matrix. Then that gives you a subset of the algorithms and so forth. It doesn't capture everything that you might learn in a numerical analysis course, but there are 2 books called Templates in the title, Templates for Solving Linear Equations and Templates for Eigenvalue Problems, which attempt to categorize this kind of stuff at a high level, and I can give you pointers later. But yes, it's hard to capture everything, but attempts have certainly been made. And some of the parallel frameworks that you'll hear about later in the semester are designed to make it easy to access sort of any row of this table. But you still have to know which row to use. Okay, so let me just say that I sorted those in a very theoretical way. I said this algorithm's n cubed, this algorithm's n squared, this algorithm's order n. That doesn't mean they run at the same speed and the same gigaflop rate. And so let me just show you some very old data to show you that the difference between n and n squared will probably dominate any small changes in the megaflop rate. So here are some attempts to solve precisely the problem I was telling you about on a 1,000 processor machine a long time ago. So this is not a very fast machine. And they took 3 of those particular algorithms. The first 2 are basically averaging with your nearest neighbors on a mesh. And the last one is, and they run in n squared time according to that table. And the last one runs in order n time. And you can see that these other algorithms that aren't maybe, don't use all the special structure can run faster. Because their inner loops, the basic kernels that they use are much, much faster because they are not exploiting all sorts of very detailed structure. So this one is running at 1800, at 1.8 gigaflops, 1.4 gigaflops. And the one that is optimal is only running, much, much slower. But the optimal one is doing only order n work instead of order n squared. So obviously you'd rather spend 7 seconds to solve your problem than 2,000 seconds, right? So you may have to, so you're willing to sacrifice a factor of 6 in raw speed in order to go that many times faster. So just to point out this obvious fact. Okay, so let me summarize these approaches. So you basically have this choice between explicit methods or implicit methods. And they both work. In the explicit case, it all comes down to sparse matrix vector multiply, which I've talked about many times, and I'll give you, technical computer science details of how to optimize it later. Or you have to do an implicit solve at every step. So you have to solve a large sparse system of linear equations. And you can either use direct methods, variations in Gaussian elimination, or iterative methods. And the ones at the bottom of the table that I showed you had both. The FFT is a direct solver, very specialized to things that look like the heat equation. And multigrid is an iterative solver. So they come up all the time. And what they all need to do is this graph partitioning in order to optimize communication and load balance. I talked about the fact that there is a correspondence between sparse matrices and, excuse me, I should have said graphs. I'm going to use whichever language is most convenient for talking about the algorithms. They're isomorphic things to talk about. And not every computation where I'm just talking to my nearest neighbors has the same efficiency. That was the example on the last slide. Multigrid ran at a tiny fraction of the speed of Jacobi, even though they were just averaging with their nearest neighbors. What really made the difference is the convergence rate. So let me close with some pictures of what real meshes look like, because in the real world, not everything is done with talking to your north, south, east, and west neighbor. And real meshes are often irregular, but a lot of the same ideas work. So sometimes people build composite meshes, which you take a bunch of regular ones and kind of glue them together to get something that simulates a more complicated object. You can have unstructured meshes, and where you have a completely arbitrary graph with connected to nearest neighbors, and if you're building a finite element model of an arbitrary object, you may end up with that. And then finally, you have adaptive meshes, because the physics is changing from time step to time step, and you have to change your mesh to match it. So let me just give you some pictures of these things. And so here is just our regular mesh again. So you're just talking to your nearest neighbors. So how do I take one of these things and combine it to make something more irregular? So here's a picture of how you might simulate a slice through a bridge abutment, right? So this is a slice through a bridge, and each of these individually is a regular mesh talking to your nearest neighbors, but obviously I've had to glue them together so that I can get something more irregular. So what does the matrix look like that corresponds to this? So what I've done here is I've color-coded that same mesh that I had before, and I've ordered each sort of rectangular submesh the way I normally would, row-wise. And so this is the first part. Excuse me, this is the first part. These are rows and columns 1 through 49. Then these comes next. These are 50 through 91. And here's what the matrix looks like. So there's the green part. That's that nice sort of band matrix that I saw before. That corresponds to that guy. Here's another blue part, another band matrix connected to nearest neighbors. Then the orange, and then the blue, and you can see it all down. But I have all these other connections there, and you can see these tiny little red dots. Those represent the fact that all of these meshes are connected to one another, and those are pretty far away from the diagonal, right? So those could be anywhere depending on who's connected to whom. So what is the impact of all of these new non-zeros that I've added on algorithms? So let me just do an example now of a direct method, which is Gaussian elimination. So here's the picture that I had before. It was on the previous slide. Here are all the original non-zero entries, those black dots. And now let's suppose I run a direct method on it. I run Koleski, which is Gaussian elimination, taking advantage of the fact that it's symmetric. Here is what in MATLAB call it spy plot, a dot for every non-zero. So all the original entries are non-zero, but look at all the red stuff. That's new stuff that I filled in. So the original matrix only had 3,900 non-zeros. This is a very small problem. And the new one has 11,500. Okay, so I've made the problem a lot bigger. But as I said, I have this reordering option. In what order should I reorder the rows and columns of this matrix? So here is a standard algorithm applied to the same problem. So these two matrices are identical. All I've done is reorder the rows and columns in a clever way using a graph algorithm called minimum degree. And so this is a lot messier. You say, what good is that? But now if I do Gaussian elimination on it, I only get the red fill in. And instead of having 11,000 non-zeros, I only have 8,000. But if I count the number of floating point operations, it went down from 296,000 down to about 200,000. So I get a large speed up in terms of floating point operations if I can pick the right order. So that's what it looks like if I have regular meshes abutted together. Here's a more typical example of an irregular mesh. This one is built into MATLAB as an example too, so you can just go look at it yourself. So here's an airfoil, and around it I put a triangular mesh, which gets much narrower when I get close to the airfoil, so it can capture the geometry and all the details of the airflow when I'm close to it. And if I write down the matrix, it corresponds to this. So there's going to be one non-zero for every vertex in this graph. And there's going to be one row and column for every vertex and one non-zero for every edge. That's what the matrix looks like. And if I do Gaussian elimination on it, this is how it fills in. So again, there are obviously better ways of doing it. This is just sort of a pictorial tour of what real problems look like. So here's another example where my original problem is this tapered tube. But the way the algorithm works is that it approximates it by something that's coarser, by taking every other mesh point, and it solves this to get a starting guess for this one. How does it get a starting guess for this one? It takes every other point again, uses that as a starting guess for that one, and finally, this is allegedly a good approximation of that as a starting guess, right? So we start with one mesh and we approximate it by ever coarser ones. This is another kind of graph algorithm that we need to have that runs in parallel. And finally, let me give you a biomedical example. So in this case, what people want to do is have a better predictor of whether elderly people with osteoporosis are going to break their bones when they fall. And so what people would like is to have a very detailed finite element model that will let them predict whether a vertebrae, like this guy, is going to be subject to fracturing when a certain force is applied. And that'll tell you, what medical treatment to have. So what people did is they took this vertebrae from a cadaver, they put it into a micro CT scanner, and with very high radiation, they made a model of this at 22 micron resolution. So this is the detailed model of that bone down to 22 microns. And you can see that bone is mostly air, right? So there's some bone material and there's some other material, and there's air. And they built a very detailed finite element model of that entire vertebrae. And there's what it looks like. It was a 500 million by 500 million sparse matrix. And there's some of the sparsity structure. And what they did was they, did the elasticity and fracture analysis, solved F equals MA for this and asked how hard can we push on it in order before it breaks. And this won a Gordon Bell Prize back in 2004. This was a big matrix back in 2004. And now this is turned into actually a startup in order to better predict, how to advise patients. You can't take the vertebrae out and do a 22 micron resolution scanner from a living patient, so they use lower resolution CT scans, but it's the same idea. So that's a very irregular mesh. And finally, let me just put up a picture of adaptive meshes. So this is a supernova explosion, and as it moves out, the interesting stuff is happening on the boundary, and so as you move, you have to change the boundary and change the mesh as it moves out. And to zoom in on that, here's what's going on. So here's where the interesting physics and chemistry is occurring right at this boundary where the meshes are. And as in this case, chemical reaction continues and this thing moves from left to right, you have to move the meshes to follow the physics. And so these are hard things to build. There's a lot of software that people have developed. You don't have to do it all yourself. And so we have to generate these meshes. You have to start from the geometric description of the object. There's a mesh partitioner has been built locally by some of our faculty, but there's lots of other tools that are available too. We have to do graph partitioning once we get it, and there's a bunch of tools for that. We'll have a lecture on it. Then we have the iterative solvers, and I mentioned a couple in passing, but we'll have another lecture on how you actually solve them given these irregular meshes. And then we'll also have direct solvers for some of them. So finally, I really am almost done. I think I've now shown you all of the original 7 Motifs patterns dwarfs. They now come up everywhere. We've now seen structured grids for solving PDEs and the irregular grids, which come from adaptive mesh refinement. And all of these other ones we saw before, all of these 7 patterns. And so we now have seen examples of all of those, and we even threw in the health application for the bone simulation. And so now, in some future lectures, we'll go back to some of these and talk about what are the right tools to parallelize them well and what are the right algorithms. So that's the end of finding sources of parallelism in locality in simulations. Are there any questions? So do we have any announcements about homework?
0 is due on Thursday, the 7th. So everyone should have filled out the survey by now. And just email the homeworks to the email address on the homework page. And we are in the process of partnering everyone up for homework 1. There was a snafu with that where a lot of the people who filled out the survey have since dropped the class. So we redid it. If you don't have a partner and think you should, then send David and I an email, and we'll make sure you get one.
Okay, thank you.